What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. Today, we're talking about elevators. This is probably coming in after we've already done our elevator lab, but if you're still confused on what elevators do and the forces that act on us in elevators, that's understandable. Elevators are kind of weird, but I think after we explain them a little bit, you'll see just how intuitive they actually are. So let's we got two trips in an elevator. We got elevator up, elevator down. During our lab, you jumped on the elevator based on where you are. I am on the third floor of this building, so we started at the top and worked our way down, and then we came back up. So we're going to start there. We'll start with the elevator up. What did we do in this lab? In this lab, we got ourselves on a scale. So we think about what we actually did inside the walls of the elevator. We stood on a scale. And when we're standing on this scale, we can look at our FBD, or the forces that act on us. The forces that act on us, of course, we're on the planet Earth. There's a weight force, which is equal to mass times baby G. And there's also the force upward from the scale. These forces are equal. They're balanced because I'm at a constant velocity of 0. And because they're balanced, we'll call this actually a normal force or a force from the scale. Because they're balanced, the normal force equals my weight right here when I'm stopped at the very top. This is true anytime my forces are balanced. Anytime I reach a constant velocity, there is no net force, there is no accelerating force, therefore my gravity, my weight, and that support force from the scale or from the ground, if I'm not on a scale, is they're equal, okay? So basically what this tells me is that the normal force when I'm at a constant velocity is whatever my scale reading is. If it says I'm 160 pounds, 180 pounds, that is my FG when I'm going at a constant velocity. We see some weird physics stuff happen when the elevator starts to accelerate, when it goes from rest to moving or from a constant speed to speeding up or slowing down. And so let's check that out. Let's think about the three different spots. We had starting, our start movement, where we started downward. We had our constant velocity somewhere around the second floor, and then we had our stopping. Okay? These are the three different spots in our motion. So if we think about what happened, here was us. When we had the scale, this is us. We'll draw our dots, our free body diagrams at the three different spots. And what we saw here is that as we started downward, the scale reading actually was less than. I'm going to actually, before I do this, the scale reading, or the normal force, was less than FG. I got on the scale, and as the elevator started to move down, it ticked downward. So if I naturally walk around at 175 pounds, I'm on that scale, boom, it ticked down to 150. For some reason, the scale, the floor, was not pushing as hard when we started moving downward. So when I go ahead to draw my FBD, I see that FG is smaller than Fn, because that is what the scale read. The scale did not read the same as it did before. Now, why is Fg not changing? Fg is not changing because, like we said before, Fg is mg. My weight is always my mass times the acceleration due to gravity. Because of that, unless I physically lose weight, I cut off an arm, I kick off a shoe, unless I actually do something physically to change my mass, my weight will not change in that elevator. My normal force, that support force, is whatever the scale reads. So in the elevator to start, this is what I saw. Why did I see it? We'll explain it maybe later, but this is what I saw, so this is what I grabbed. After I've started moving, by the time I reach the second floor, what I notice is the scale gradually moves back to that original weight force. It matches my weight halfway through, which must mean I'm now moving at a constant velocity, because again, if these forces are equal, there is no acceleration on the object, on myself, okay? Which makes some sense. I start moving, I reach a constant velocity, and now before I hit the ground, I've got to stop moving. And I can think about what might need to happen when I stop moving, or I can look at the scale and see what did happen. And as I approach the ground, that normal force is now greater. It is reading a larger value than my weight force. So if, again, I walk around at 175 pounds, that scale read almost 200 pounds. This upward force was larger on me to slow me down. These were the three different points in my motion as I moved down, okay? As I moved up, let's see what happens. I started at the ground. Now I'm going to start down here. I'm going to see a constant velocity somewhere on the second floor. And up here, I'm going to be stopping. Moving from the ground up. Let's start with our three pictures. 1, 2, and 3. I'm going to go ahead before I even start this problem and say all of my FGs are the same because my mass is not going to change while I'm in the elevator. So I'm going to say all of these are equal, and we can actually call all of these equal over here. FG doesn't change in this entire trip. So what did the scale read? Well, when I started, that normal force ticked up. The normal force, the scale reading, was larger than my weight force. My mass, or my apparent weight, ticked up. Not my mass. My apparent weight on the scale ticked up. As soon as we got to the second floor and reached our constant velocity, our normal force, our scale force, gradually moved back towards where my actual weight is. And as we got to the top, we saw it ticking down of that scale reading. The normal force got smaller. Now, what I challenge you to do at home is pause this video and explain why, or explain how the net forces on all of these are agreeing with start, constant velocity, and stopping on both sides. Pause it here. Go ahead and explain to yourself, using your models, your pictures, your FBDs, why this would be starting upward, why that would be stopping upward, why this over here is stopping downward, and why that is starting downward. Pause it, explain it to yourself, write it out, because I'm about to do it. Here we go. Over here, what I see, if I go ahead and write my F nets for these different experiences, they look the same, in which gravity minus Fn is equal to m times a. Yeah, I can explain this using my net force equation. In each and every one of these, I see Fg, I see Fn, and again, this time I'm going to say Fn minus Fg equals ma because Fn is larger. But basically I get the same F net equation all three times. There are differences in the accelerations, but they're basically the same. Okay? Let's start with the middle one, which I think is the easiest. If we're at a constant velocity, these forces are the same. My acceleration is 0. Another way of saying acceleration is 0 is saying there's a constant velocity. This helps explain my picture. My pictures show constant forces or equal forces. Therefore, there's no acceleration. Therefore, I'm moving at a constant velocity. Got it. How about at the top? At the top, I see that the gravity or weight force is larger than my apparent weight or my normal force. Because Fg is winning, my acceleration is going to be downward. If my acceleration is downward and my velocity is downward, I'm speeding up. That's what's happening there. I start at the top. I move down with the downward acceleration. I start to speed up downward until I reach a constant velocity. However, if my velocity is upward, like it is when I go from the first floor to the top floor, what I see over here is a slowing down. The acceleration is still downward. The gravity force is larger than your normal force. But because I'm going up and my acceleration is opposite that, I see a slowing down, which also makes sense. I'm going from a constant speed to my final position. I need to slow down until I get to that third floor. Let's look at the bottom now. These are similar FBDs. They have the same F nets, but they warrant or have a different outcome. This acceleration here, because Fn is winning, this acceleration is upward. When my velocity is also upward, I see a speeding up. That makes sense. If I get on my elevator, stand on my scale, and go to the third floor, I have to speed up to a constant velocity before I slow down and get to my final position. That's how the elevator works. And now my FNet, my FBD, and my conceptual understanding all link up. They are all making sense to me now. Over here, if I'm on my way down, acceleration is up, but my velocity is down as I go from the third floor to the first floor. What I see is a slowing down. This also makes sense. As I come from the third floor, speeding up to a constant velocity, I'm going to have to hit the brakes as I slow down and come to my final position on the first floor. We can take this a step further, right? We can take all of this acceleration and position information and actually graph it in a VT graph. And that's what I had you do on the lab. So let's go ahead and do that. Let's graph what this might look like on a VT graph. Let's go on the way up. We'll graph VT on the way up, and we'll graph VT on the way down. VT, VT. On the way up, let's start on the way up. On the way up, my initial velocity is 0. You hop on the scale, push the button to go to the third floor. Initially, you're 0. You're going to speed up. In which direction are you speeding up? In the upward direction. We go from rest. Our acceleration is upward. Our velocity is upward. My velocity is going to get more and more positive at a constant rate. So I see a constant increasing velocity until I reach my cruising speed or my constant velocity, at which time my velocity stays constant. There is no change in my velocity. Eventually, though, I need to slow down and come to a stop at the third floor. And when that happens, my velocity has to get back to 0. I see this kind of trapezoidal curve. Maybe it's smooth. It's probably smoother in actuality. But this is a pretty good assumption, a pretty good prediction of what's going to happen based on the forces that are applied to me, if these forces are constant forces. On the way down, we can do the exact same thought process. You can pause it here and reason your way through the down video or through the down graph, or follow along with me. But when we're moving downward, we start at rest. And now that velocity and acceleration are both downward. I'm going to get faster moving down. So I see my graph increase in the negative direction until I reach my constant velocity moving downward. I'll see a flat, a non-changing velocity. And as I reach the ground floor, I see myself slowing down. The acceleration goes up, so I should see a positive VT slope as that velocity approaches 0 or approaches rest again. These are the up and down VT graphs. Could I graph acceleration time? You betcha. Could I graph position time? That'd be a fun problem too. I could also do those things. I don't ask you to do those things on our lab, but I certainly could ask you to do those things. Okay, recapping. Let's recap. Can you, first of all, do you understand what a scale reads? Do you understand why we stood on a scale in the elevator? Scales will only read weight under certain conditions. Next thing, can you model the forces that bring you either from the bottom floor to the top floor and from the top floor to the bottom floor? Can you model those forces on an elevator or on you in an elevator? Can you write their F-nets? Can you determine whether or not you're speeding up or slowing down based on the accelerations you feel and the velocity, direction of velocity that you're moving in? Lastly, can you graph these things on a VT graph? Do you know how the kinematic graph relates to this motion here? Okay, these are the big takeaways. I do have one challenge question for you. One just kind of like, whoa, I saw this weird thing one time, and I want to share it with you. So here it is. Story time. Mrs. Gustin and I, a couple years ago, were on vacation. We were on vacation. We were headed out west. We actually went out to Utah to do some camping and hiking, but we flew in to Las Vegas, Nevada, which is a really nice spot to go out to the west because it's pretty cheap to fly into. Anyway, we're out there. We stay there for the night, find a really cheap hotel in Las Vegas for the night before we pick up our RV and go out west. Anyway, this is wild. This is absolutely crazy. We get on our elevator. I'm not a very good artist, but here's the elevator that we get on. Right? The elevator is shaped like a box. We can go here are the doors. Right there, you can see the doors. Here's the elevator. This is us hanging out in the elevator. There it is. The doors, though, are right here. Okay? We get on the elevator. I'm standing here in the elevator, and my suitcase, which is on wheels, is right here. Okay? Now, I'm thinking, I'm going to go up in this elevator. What actually happens is wild. All right? What actually happens is as we push the floor, I forget what floor we're staying on. I think it had to be more than like 2 or 3. I think we're on like floor 18 or something. Something really tall. I don't know. We're way up there. We hit the button to our floor and we go. And as soon as the elevator goes, think about it, right? I'm thinking normal force, going to accelerate us upward because we're at the ground going up. Here's my weight force. I'm thinking I'm going to experience this type of force. Instead, my suitcase, which is on wheels, as soon as this elevator takes off, does this. It rolls all the way to the back of the elevator. It doesn't press down. We don't get pressed down. We feel this like, whoa, lurching backward, and my wheelie suitcase, shoom, flies to the back of the elevator. So is that part of this? No, but it's a cool real world example, and I want you to think about it. If you have an answer, you can comment it. If you have an answer, go ahead and bring it into class. We can talk about it, but it's a really cool, weird thing that happened. So why did it happen? Why would it have happened? Like, what was going on with this hotel that would have made the elevators have to move in a way so that my suitcase rolled back? Those are all questions you can answer either in the comments or come and talk to me in class, all right? So think about it. Till next time, see ya!